Hello, Sacke here, back with another Genshin Impact video. Today, I will be doing the follow-up to my most recent video, the physics of arrows in Genshin Impact. So, what's the main point of this video? The point of this video is that I'm going to see whether or not the model I presented in this video is correct or not. I'm not going to figure out why, and I'm not going to fix it in today's video. I don't have the time to do that at the moment. I need to do a lot more stuff before I can give a proper model if it is incorrect. But it has come to my attention that from a commenter named Daggerball that the model may potentially be incorrect. And I'm saying potentially because I also would like to confirm it for myself. And well, yeah. The point is, we had a little bit of a talk back and forth. I give him a lot of credit because he actually did some pretty interesting experimentation to actually check my model. And it seems like my model does not accurately predict what should happen in game. I'm just going to check and verify that that is true, and if it is true that my model is wrong, I will have to hold accountability for that, as well as especially considering how many people watched the video and how well received it was. I have to make that clear. If I am wrong, I am so sorry to everyone who watched that video. At most, I can just hope that you learned more about physics in that video. I will try to eventually fix that mistake if it is there, but whatever the case, I'm not sure. I'll have to verify it for myself. So yeah. There are actually two comments that I actually want to go over. One of them is from Daggerball and another one is from Prontab. I mentioned Daggerball first, but I think I should also mention Prontab's comment. It's about R-arm. And well, if you know anything about the previous video, I measured R-arm to be negative if you take a look right here, so yeah. R-arm is negative, you can see right here. Granted, it does have a huge 95% confidence interval, but it's whatever the point is, it came out negative. And well, what Prontab is actually suggesting is that it might actually be 0. Instead of the arrows spawning at the tip of the player's arm, what Prontab is actually suggesting is that the arrow actually spawns at the center of the character. And well, at first I was a little skeptical of the idea and I didn't really accept it. However, once he brought up this little argument here, in terms of game programming and game development, essentially, it actually made a lot more sense. I've done a bit of Unity in the past, so I do know a little bit about game development. Just a little bit. Granted, I don't know about the full development of a game because I've never been able to do that, but I do have a bit of experience about game development. They mentioned something about I bring this up because I think Genshin does something similar to what shooter games do, and it messes with collision and your ability to clip your model into geometry, and it does some visual hacks, like hide the arrow when it's first fired in third person so it doesn't look like it's inside the player model to make the aim mode experience make more sense. It's a gut feeling based on your observations, and it reminds me of the struggles first-person shooter game devs have with like rendering your hand/gun and where bullets emit from your model versus your reticle. I did not measure time the first frame that the arrow was visible. I actually considered the first frame the character animation plays. Actually, I'll just show it to you on screen because of editing. You cannot see the arrow at all. You just see that the bowstring is just kind of disappears. It's not disappeared, but whatever the case is, it changes position and whatnot. But you don't see the arrow. And that is actually another thing that made me think about it. Let me go ahead and try to draw this out so that way it might become a little bit more clear as to what I'm saying. If you remember from my previous video, I considered this length right here, all the way up to the tip, to be our arm, specifically defining it to be positive as it is a radius of a circle. So this is positive and it points in this direction. But because it's negative, maybe what it was suggesting is that it actually starts at the center. Some other commenters have actually pointed this out, but Prontab is the first one that actually mentioned it. And in fact, if we assume that the camera pivot is there, this is again something that comes from Prontab's comment. We have a camera, and we can assume that that pivots about the center of the character. And what Prontab is suggesting essentially is that the arrow, upon firing the arrow, it will be invisible. It will travel from here, but it's invisible for as long as it's traveling this distance. However, at this point, it becomes visible and you start to see the arrow. So that's what he is suggesting. So here, invisible, here it's visible. I'm going to, from this point on, assuming that you're using the same exact time measurement scheme that I'm using, which is upon the first frame of animation, I will set our arm to 0. So that's the first comment out of the way. Now for the main one, the one with my little conversation with Daggerball. What he's saying is if the equations are correct, the maximum shooting range should be about 505 meters on flat ground. First of all, how do we actually even get that number? Let me go ahead and write out the equations. Now, earlier we established that I'm going to be using our arm is equal to 0, so this one just goes away. I think it's also important to remember the values, so we have that VI is equal to 50 meters per second. Then for G, I believe that should be 5.345 meters per second squared. And lastly, TA, that should be 0.525 seconds. Now, how do we actually, get something that we can predict? Well, Daggerball used the maximum shooting range of 505 meters. The first thing that you need to ask for solving this is, what is the optimal angle? If you're dealing with a very simple case, well, let's think about it. We know that for sure T must be greater than TA, otherwise the arrow is pointed directly to the ground. So yeah, that condition. So we're going to say that y is equal to negative g times t minus ta squared, divide that by 2, plus the initial vertical velocity times t plus yi. For yi, we can just assume that the player is on... We're just going to assume that this is going to be equal to 0. For those who would say that it's equal to 45 degrees, that is actually not true. In fact, I only realized this very recently, despite having doing projectile motion for years. That is only valid for the situation where you have this sort of equation, g plus biyt. It's really only valid in a specific case. The actual way to determine the optimal angle is, well, calculus. You're going to have to essentially find the derivative with respect to theta of x, and then set that equal to 0. You'll get some sort of equation, and then you can solve for theta from this. Now, the thing is, it's actually really hard to solve this expression, at least generally. So if we start off with Vix times t plus xi, this one's actually pretty simple. The derivative of a constant is 0. Then the derivative of this, well, we have to remember that Vix is equal to Vi cosine theta. What's the derivative of cosine theta? Well, that is equal... Actually, we should do a bit of the product rule first. So I'll do t times d theta Vix, and then we add that with Vix times the derivative of t. We also set that to 0 for calculus reasons. So then we have multiply that by time, vi times sine theta, when we take the derivative. When you take the derivative of cosine, that is equal to sine theta. Then for this one, we have vix times the derivative of time with respect to theta. This term is really, and I mean really difficult to solve for. And then on top of that, you will then have to solve for theta. It's not a pretty expression. I'm going to tell you that right now. I tried to look at it and then I realized that it's not going to work out. So instead of actually doing this, how about we just use an approximation? Let's just use Desmos. So here I am in Desmos. I basically encoded all the parameters. We have G, we have TA, we have VI. This is going to be the angle theta. I mean, you can use like this, but I'm just going to use capital O for that. Then we have YP. I'm just using the female model, all-female model with a YP of 1.4 meters. So yeah, in this case, we calculate VI, VIY, and VIX, and then we can just plot it. Now, we have to be a little careful about this. Let me hide that for a second, and let me zoom in. We have a height versus time graph. However, we're not really exactly interested in the height versus time. We want height versus horizontal distance. Instead, what we have to do is to take advantage of the relationship that in this case, this is going to be equal to 0 because our arm is equal to 0. So from here, we can see that our time will be equal to x divided by vix. From there, we can substitute for time and get this expression y in terms of x. So if we do that, we get a very interesting expression. So there we go. All the way out. So yeah, that's a pretty far distance if you ask me. Point is this, we have this sort of equation. Now, obviously, as I change theta, the distance will go farther, and if I lower theta, it goes smaller. But there's a limit to this. If I zoom out farther and farther, you'll notice that eventually it just starts to go backwards. Instead of extending farther, the trajectory actually starts to recoil backwards. So maybe it's actually a little bit smaller. And let me take a look at something here. So we have 45 degrees. If I go a little bit further down, so we have 45, if I go down to 44, the distance is actually just a little bit slightly higher. So just by that, we actually already proved that it's not the optimal angle. That is only applicable if we set this to 0, yp to 0, and ta to 0. And when that is true, well, the optimal angle will be 45. So what is the actual optimal angle? Well, so basically this entire huge expression, you get that from solving this equation for t. So if you solve for t with this equation, it takes a bit of work. Essentially, you just got to use the quadratic formula. You will eventually arrive at this solution. Now, this solution will tell you the time. This will tell you the time it takes for the object to hit the ground. Then, if we multiply that by vix, we'll actually get the distance that the object would travel. However, instead of trying to inputting exact values for viy and vix, what I'm instead to do is to graph this function t as a function of theta. But you might notice that between the values theta is equal to 0 and theta is equal to 90, there's a maximum point. It's about 43.85 degrees, approximately. So if we take that exact number and input that into our value for theta, we will actually get the maximum, that's not the right one, we will get the maximum value for our distance. That's pretty much what Daggerball said. 505 meters on flat ground. So that is actually how we get it. In fact, he also did use Desmos too. Anyway, enough about that. Let me now get into the testing. Alright, so here I am in Genshin Impact. What I'm going to be doing is essentially trying my best to aim with the correct accuracy. It's a little difficult to say because, well, I'm sorry, it's a little bit difficult for me to aim accurately. I cannot tell if I'm aiming accurately. So right now, I can use this platform for as reference for 0 degrees, but to figure out what's a 45-degree angle, I don't think I'm the best judge of that. Now, how exactly am I going to measure the distance? We'll first see if the time matches up. If the time doesn't match up, then we already know that something's wrong. Because measuring distance is a lot more tricky because of how far arrows go. I mean, take a look at this. You mean to tell me I can easily measure that? No, I cannot. Alright, so first of all, let's go ahead and do the measurement for time. I'll go like this and fire. Alright, I'll see you in my video editor and we'll see if the time matches up. Alright, so here I am in my video editor. I'm going to drag the clip in and I'm going to change the frame rate. I'll put it here, so put this clip here. Let it load. And I'm going to mute the audio tracks because we don't really need them. In fact, I might as well just get rid of them. Alright, there we go, no audio. All we gotta do is go to the end of this pretty long segment. Let me go ahead and try to measure it. Okay, so here we go. All I'm gonna do is rewind. Alright, so okay. Notice that on this first frame, the arrow is technically not visible yet, and the frame, like, immediately after, the arrow is fired. So that's just something cool. So here we go. Anyway, let me just double check. There we go. The arrow is gone, so I'm gonna make a cut on that frame. Next, we're just going to wait until that hits the ground. So let's focus really hard over here. Not get distracted by anything else that's happening. It's going to be a little awkward to see because we also have these particles happening, but it should be pretty obvious when it hits the ground. Oh, there we go. First frame of impact. And there we go, we can measure the distance, and I'll do that in frames. We have 90 frames. Alright, so I'm back in my drawing program. I'm just going to indicate here that time was equal to 90 frames. So let's convert that to seconds. It's not too hard to do that. So we have 60 frames per second. So this is exactly, we'll cancel that out. That's 2. And this one is 3. So we have exactly 1.5 seconds. So that's our time. Next, we have to actually see what our model predicts. Okay, so in this case, we actually have to consider that the platform, let me go into edited mode, these platforms that I stand on are about 1 meter off the ground. So let me head back onto my desktop here. So we know that y naught is equal to 1 meter. Then we also consider that the player model that we were using is the medium female model, in which case that means that we have extra 1.2 meters. Oh, and in fact, we actually set this to 0 because we're going to hit the ground. And then you can essentially solve for t. I'm just going to use my calculator here, so give me a moment. My calculator actually estimates a time of 1.43 seconds. Okay. there's a bit of a discrepancy, but, well, that could actually easily be attributed to like error or something. It's still, I think it's still within reason, but you also have to remember, I used this height for my data. So instead of just measuring the time it takes for the arrow to hit the ground, why don't we consider something else? In fact, I'm gonna try to move this down here. Then what I'm gonna try to do is use a barrel to do this. So I'm gonna put the barrel all the way on the ground, and I'm gonna try to align this as best as I can. And I'm gonna put this at some distance. We'll try to align it like that. And I'm also gonna move it over closer to here, that way I don't have to run. Let's actually just use our calculations to estimate the distance. And we get about 71 meters. Wow, that is actually pretty big. So 71.615 meters. So I'm going to put this at a distance of 71 meters. I don't actually know if that's 71 meters or not. Maybe closer to 72 would be more appropriate, so that's pretty close. Alright, so let's now go ahead and test it. So first of all, I want to set it to daytime so I can see better. Then I'm also going to go into my settings to lower my key bindings. Let me go audio, where is it? Controls, there it is. Horizontal and vertical sensitivity. Go right here, and we'll slowly aim our bow like just at the top of that, and then we're gonna push it slightly to the side. And theoretically, I might miss it, but oh, huh, it actually hit. Okay. That's interesting. Okay, so it hit. For this first experiment, it seems like it's pretty accurate, actually. I'm still very doubtful, though. I want to go ahead and check this for farther distances, but that's actually really difficult to do.
Lot of boring math later.
Alright everyone, so I think I finally have an experiment that can help test my model. I can probably actually even use this in the next video where I do physics of arrows. So essentially, the problem I was having is that I had no idea how to measure angles with a high degree of accuracy, or a relatively high degree of accuracy. It is a little difficult to see, but this little red line here, that's the trajectory of the arrow. And here we have a little explosive barrel. So essentially, we'll position the player at some distance to this explosive barrel. And that distance, we'll just call that, actually, instead of D, this distance will be X. So the thing is, X needs to be pretty large. And a problem that we have is that, you know the Twang Bang Bang minigame, how it shows you the distance? It will be like, it will tell you like, oh, you're like 1 meter away. Oh, maybe it says you're 3 meters away, or like 10 meters away. The problem is, if the distance is greater than 120 meters, this thing will just disappear. It will not show you the distance anymore. This barrel method is only useful when you're dealing with distances that are less than 120 meters from the explosive barrel. That's a bit of a problem, because now we need to be able, so we somehow need to be very far away from the barrel, but we also need to know the distance to it. And, well, let's just say that walking that entire distance is not exactly the most ideal way to do it. So what I'm going to do is actually make use of the technique that I will be doing in my next video, which is measuring distances with the map. So essentially, I'll just I'll take a screenshot when the player is positioned here, and I'll take another screenshot when the player is positioned at the explosive barrel. That way, I can then measure the horizontal distance between those 2 points. Now I need to figure out, what is the angle? Well, for the angle, we know that the player will be some initial height off the ground, that's why not. And we also know that there's the YP of the player, which in this case I'll be using Yellon. So YP will be 1.4 meters. But the important thing is actually this third platform right here. This third platform is going to be what we use to determine the angle. And I'm going to use this little edge, the right edge, this edge over here, to try to indicate the angle I should aim at. So we have this little right triangle right here. No, it's a little hard to see, so what I'm going to do is put it off to the side, or to the bottom actually. If you know about anything about trigonometry, you know about SOHCAHTOA. This is a mnemonic sort of thing. O is opposite, H is hypotenuse, and A is adjacent. So notice how our angle here is this. The opposite side will have to be this one. So whatever the height of this is, we can make use of that. That is going to be the opposite. That will be referred to as opposite. Then there's also the adjacent, which happens to be the side that it's touching that isn't the hypotenuse. This one is the hypotenuse, so the adjacent has to be the bottom one. What we can now use is this TOA, which is tangent, the tangent function. So the tangent is specifically the opposite divided by the adjacent. So opposite, that's delta y, and divide that by the adjacent, delta x. And there we go. We now have a way to actually measure theta accurately. You just make use of the arctangent function. Something to note about this arctangent function, you might also see it written out as tangent inverse. We have a way to now measure angles, and we have a way to measure the distance, and what we can do is check if this angle is correct. If it goes like this, then well, yeah, our model is not correct. If it does like this, well, yeah, our model's not correct either. It needs to hit the barrel and needs to explode. So yeah. Now, how exactly do we measure delta y? Delta y is pretty easy. We already know the height of the platform. And the height of the platform is going to be equal to YA and YA. Yeah, that's the reference platform for the angle, this one here, this one on the top. Then we just subtract it by the YP and Y naught. So minus YP and Y naught. There you go, that's pretty easy. Now for delta X. Something I would also like to note is that the character will specifically be positioned at the edge or the back side of the platform. They will not be towards the front, they will not be in the middle, they're towards the back. The reason why I'm doing this is because I can make use of the fact that we were able to measure how long one of these platforms are. So I'm denoting that as XA. And you also can see here we have one platform and two platform. So this third one that's up here is 2 times XA away. And therefore, delta X is equal to 2 times XA. So you have 1 XA, 2 XA. There we go. Alright, so I've done the measurements, and well, for XA, what I did is I simply just took Yellon and we just walked. So, you have this little clip right here, and that clip is 227 frames long. So with that, we can very easily obtain the distance, which came out to be about 4.631 meters. Maybe it's more closer to 4.6, but whatever. I'll just use the whole number. I'll just use this. Then for the distance, that one is a bit more difficult to explain. In fact, I mean, there's a reason why I'm going to make a whole video dedicated to it in the first place. I just essentially did the pixel measurements, and here I combined 2 different screenshots. So one of them's here. Okay, I kind of just deleted that so that way I'll be able to see the underside of the I'll be able to see the arrow into one single image. Technically, you don't need to do that. You could always just leave the opacity of one layer smaller. And essentially, I have this little line between the 2 points, and if I go here, then under distances, enable that, we have this 702 and 428. Those are the distances you can see here. Right, there it is. So yeah, that's the distance in pixels, and then I just convert that into a number of arrows. The arrows simply refer to the blue arrow, this blue arrow here. So this arrow distance here is about 8 meters, more or less, or 8.5 closely. Whatever the case is, I just measured it, and yeah, it comes out to about this distance, and that will be our x. We can now take these numbers and put them into our equations and then solve for the angle. So yeah, let's go ahead and solve for it. Alright, so after plugging that into my calculator, I essentially get this answer. I get 4.111 seconds. And now to solve for t, all we gotta do is take this value and plug it into here, to the t over here. So theta is simply equal to 32.643 degrees. Now, obviously, I don't think I'm going to be able to get that level of accuracy when I measure it, but the point is, now we can solve for delta y, which is what we need in order to actually calculate, to be able to determine the angle accurately. And we get 8.333 degrees. Or not degrees, sorry, meters. And with that, we should be able to see if it'll hit or if it'll miss. Alright, here I am in my teapot, and I'll just go ahead and set up everything. I think that should be safe enough to the point where, you know what, I'll move this one up as well. So hopefully it will not hit. So let's just double check before we actually do anything. So if I aim like right there, it should. Oh gosh. I hate this. I hate it so much. Okay, so you know what? Here's what I'm going to do. I'm just going to see if I can shoot it, and then if I can, and then I'll see if the angle matches up. So let's see if I shoot at an angle that's much smaller, it's a little difficult to see. So let me try to aim like this. Lower. I can just barely see it, like right. Ah, there we go. So whatever this angle is, that is what it is. So okay, I don't know if there's anything I can do about this. Like, can I measure anything? But if anything, there's something wrong here, because clearly it's saying that I should be aiming up here, but the angle is more closer to like down here. So there's definitely something wrong. Let me just at least double check that the time, if the time matches up. So yeah. Supposedly that's 216 frames, and if we convert that to seconds, that's 60 frames per second. This comes out to be 3.6 seconds. So there is definitely a discrepancy between our models. The angle is not correct and the time is not correct. So we can definitely say for certain that there is something wrong with the model. I don't know exactly what is wrong with the model, I will have to do a lot more testing to figure out what might be the true model. Unfortunately, that is going to have to wait for a bit of a while because I'm currently more focused on the measuring distances with the map video. The point is this. This equation is wrong. This model is wrong. It does not predict accurately the time, as we saw here. It does not accurately predict the angle, so this is wrong, and it does not accurately predict the time. So what could possibly be wrong? Well, for one, G could be wrong. I don't know if it's wrong, but I don't know what exactly is wrong. It could be G. Another one could be TA. Maybe TA is wrong. If that's not it, then maybe there's something wrong with our initial assumption that the horizontal velocity remains constant even after TA seconds. So those are some possibilities I leave out. Maybe this maybe Vx at a time greater than TA does not equal to Vix. If we consider the possibilities, it's either that G could be larger than 5.345 meters per second squared. That's one possibility. It could also be that TA is less than 0.525 seconds. It could also be that this scenario, where t is greater than ta, does not equal to the initial velocity at x. Technically, it's also possible that vi is actually less than 50 meters per second, but I personally don't think that's very likely. I think that this is a very reasonable measurement, as you saw from my previous video. Because if you remember the plot, you know what? I'll just open. The lines very much match up with that 50 meters per second slope. The slope is pretty good. I think that this one is unlikely. I'll consider these two possibilities, but I also think that this is also a reasonable possibility. Whatever the case is, this equation, it does not hold for time greater than ta, whatever ta may be. And I would like to apologize to all of the people who have watched my video about modeling the charge shot physics, because unfortunately what I presented was not correct. Though again, science does not always get things right, and over time we learn how to correct things. It is a bit of my fault for not actually, verifying the model first, but at the same time, that video is getting very, very, very long, and I didn't really have many ideas for how to verify the model. So I will try to find the truth, and I need to collect a lot more data to figure out the exact reasoning for why there's discrepancies between the model and what we see in Genshin. So, yeah, unfortunately, the equations that I presented are not correct for time is greater than ta. If the time is less than ta, well, the equations are going to hold. It's literally moving in straight line motion. You can't model that incorrectly. I mean, seriously, all that is just Vix times t, and then y is equal to Viy times t.
16 paranoia-filled days later.
Alright, so I decided I didn't want to take any chances with assuming that these equations are true when they actually weren't, so I did an experiment. Yeah. So essentially, I just did something similar where I took a bunch of platforms. In this case, I have 4 of them. 1, 2, 3, 4, whatever. They're equally spaced, whatever. Something like this, and then I put a platform right here. Then, of course, stand at the edge over here, and fire a shot. Fire a charged shot towards that object and see how long it takes for it to hit it. Of course, we also have to consider the angle, theta, whatever, and yeah. Pretty much almost a similar setup here, except we have 4 platforms, and this is just the length of one platform, so multiply that by 4, we get this distance. Then I just put it at a height of 7 meters, and this one is like 1 meter off the ground. And then this one here is YP, so yeah, that's where we get these two, and that's where we get these two values. Next, what I did is calculate the angle for that, which should be about 13.946, and then I also took the time to calculate the horizontal and vertical velocity. If we take delta x and divide that by vx, or if we take delta y and divide that by vy, we will get about 0.382 seconds. Now, if we convert this to frames, we get 22.9 frames, and that's pretty much 23 frames. In DaVinci Resolve, I did the thing, measured the time. So here it is. I'm just gonna mute the stuff. Here we go, and there it is. I took a shot at the platform, and it hit. So we measure exactly 23 frames. So this equation here is correct. Yay! I would also like to apologize if the video editing for this one is very erratic. Let's just say that I was coming up with a lot of the stuff on the spot. I did not have any ideas for how exactly I would do things. So if my editing seems like a bit all over the place, I really apologize. Usually, even when I do these videos where I do live commentary, I have a bit of an idea of a structure for everything. And I really apologize for that. And, well, yeah. That's really about it for now, so thanks for watching and hope you've enjoyed.